This is problem 1-48M. It's on page 46. A circular bar carries a series of loads as shown in figure P148. Compute the stress in each segment of the bar. All loads act along the central axis of the bar. So if you haven't seen this problem, you should definitely go to page 46 and look at it. I'm not going to redraw it here. It's a fairly simple thing. Essentially what they're asking us to find is the stress in section AB, the stress in section BC, the stress in section CD. So there's three different sections, and you'll notice the first two sections have the same diameter. From AB to BC, the diameter of the rod is constant. It's just there's a load applied at B. Now CD is a smaller diameter, and so we have to take that into account. That'll change our stress calculations in that area. But all of these are just going to be normal stresses because the load is parallel to the normal of the cut surfaces. If we were to cut the rod and look at the areas along the way. So what I did first is I calculated the area of the rod in section AB because it would be the same as the area in BC. Again, it's just a round cross section, so it's pi d squared over 4. And so this is pi times 0.025 meters squared divided by 4. That's the diameter of that section, is 25 millimeters. This comes out to about 4.9087 times 10 to the negative 4th square meters. Calculating the cross-sectional area for CD, you get pi multiplied by its 16 millimeters squared over 4. That number comes out to about 2.0106 times 10 to the negative 4th square meter. So there's the area in the various sections of this rod. Now the force in section AB, if you were to think or imagine a free body diagram of the rod in section AB, you'd have all the stuff to the right of A. And so basically the material at the wall has to pull back on the rest of the rod to resist all the forces on the rest of the rod that's trying to pull it away from the wall. Now it turns out there is one force that's actually pulling away, and it has magnitude 4.45 kilonewtons. It's pulling to the right. The other two forces are actually pushing to the left, so they're compressing the rod. And so there are the other two force magnitudes. Notice these two are compressive, tending to squish the column, whereas this is tending to try and pull the column away from the wall. So the net effect of all these forces is that section AB has to support a compressive load of 17.52 kilonewtons. I'm just going to write C for compression. I'll use C for compression and T for tension. Now in section BC, we don't have this force, right? This force is applied back at B, and so if we're cutting the rod at BC, then this force is not there. So then it's just negative 12.32 kilonewtons minus 9.65 kilonewtons. So basically section BC is under even more compression than AB. In fact, the sum of that is negative 21.97 kilonewtons, and that of course is compression again. Now section CD is even further out to the right. It's in the smaller diameter section. There the only load applied is this compressive load of 9.65 kilonewtons. Negative means that it's compressive. So there we go. So that was pretty straightforward. We've got the areas in all the sections. We've got the forces in all the sections. And so now all we have to do is calculate the stress. So stress in AB is a normal stress. It'll be the force in AB divided by the area in section AB. That's negative 17.52 kilonewtons divided by 4.9087 times 10 to the negative 4th square meters. And anyway, that comes out to about 35.7 megapascals. So there's one answer. The stress in section BC is the force in section BC divided by the area in section BC. That's negative 21.97 kilonewtons divided by a cross-sectional area that's the same, because the cross-sectional area in A, B, and BC are the same. So 4.9087 times 10 to the negative fourth square meters. So that comes out to about 44.8 megapascals. And then finally, the stress in section CD is the force in section CD over the area in section CD. Now the force in CD may be lower at negative 9.65 kilonewtons than, say, the force in either of the other two sections, but the cross-sectional area is less. That means that there's more opportunity for a higher stress here. Let's find out what we get. So the area in CD is 2.0106 times 10 to the negative fourth square meters. Plug all that in your calculator and it's about 48.0 megapascals. Now I should have written that, all of these stresses are compressive stresses. At this point in your understanding of mechanics and materials, you may not realize that that's important, that the compressive thing is important. But some materials respond to compression better than others. Concrete, for example, is not good in tension, but it's good in compression. Steel, it doesn't matter. You get the same kind of behavior essentially in both. Now, of course, the issue is that if you have a member that's long and slender and it's compressed, then it can buckle. But we'll learn about that later in the course as well. So it's interesting to notice that the section that has the lowest stress or lowest force in it actually has the highest stress, and the reason for that is that it has the smallest cross-sectional area.